Okay, so we're going to look at additional displays of quantitative data, particularly XY graphs. And the first one is a frequency polygon. Now, just so you know, there is a variation of a frequency polygon if the vertical scale is going to use relative frequencies. And remember, relative frequencies are very closely related to percentages or proportions. Then that's a relative frequency polygons are variations of the frequency polygon. You're just going to be using a different vertical scale. All right, so the frequency polygon, and I'll show you how it's linked to a histogram in a little bit, but what we're going to use is these points. And so it's useful to, when you're interpreting a frequency polygon, just to write down the coordinates of several of the points. The ordered pairs that we're going to use here are of this form. The x coordinate is the midpoint of a class. And the y coordinate is going to be the frequency or the relative frequency. So in this case, we're just going to use the frequency. Now you can see various points on this graph. So I'm going to write them down and show you how those points are related to the classes so that in the problems that we read later, we can interpret them. Now, there are 2 points at the beginning, or beginning and the end. The beginning point is some midpoint that's not part of our graph, and 0. And that puts the first point on the x-axis. The ending point is also going to be a point on the x-axis. That's this point and this point. Those are not actual points that make up classes, but those are always points that we add at the end of the graph so that we can always start on the x-axis and end on the x-axis. The beginning point where you would put it would be on what would be the previous midpoint, and the ending point would be the midpoint that comes after the last one. I'll just call it the next midpoint. I'm going to write down the coordinates. That first point is -2, 0, and the last point is 26, 0. So that would be the beginning and the ending point. It's just to add a couple additional points at the beginning and the end so that our frequency polygon begins and ends at 0. Now, all of the middle ones are going to correspond to different classes of data. So I'm going to write down some points. So there's 2, and that point right there looks like it goes up to about 72. And I'm going to just quickly go through and write down the rest of them. Sometimes it's a little tricky to determine the exact y value that you want to use, and so you'll have to estimate it. So if your points are off 1 or 2 from mine, that's fine. All right, so 655 is the next one, and then 1019, I'll call it, and 1411, 18.1, and 22.2. So those are all the midpoints. And if you add up all those midpoints, or the number of points there are, not the first and the last one, but everything in between, we have 1, 2, 3, 4, 5, 6. So there are 6 midpoints. And so there are And remember, this is 6 midpoints, not counting the first and the last. So that means that there are 6 classes. So to help us answer the questions below, and you might not need this table, but I think it's useful to go back and forth between the graph and the table. We're going to have the class here, and then the midpoint. And the midpoint is needed for a frequency polygon. And then the frequency. Now the midpoint and the frequency, they make up the points. So I'm just going to put all these midpoints in here. Now we have 6 classes, and 272 is this point here. It's the midpoint and then the frequency. And I'm just going to go in order and write all these down. The X and the Y coordinate of each point, the pair, midpoint, frequency. Now, if you note the distance between one midpoint and the next, in every case, you jump by 4. So from 2 to jump to 6, you have to, so you have to jump by 4. And from 6 to 10, you jump by 4. And so everything is jumping by 4. So since everything jumps by 4, we're going to say that the class width is equal to 4. Well, if the class width is 4, and the midpoint of the first class is 2, then this class must begin at 0 and end at 4. From 0 to 4, its distance is 4, and then right in the middle between 0 and 4 is 2. So this first class would be 0 to 4, with the midpoint 2 being right in the middle. Now every other class after that also has a class width. So the next one goes from 4 to 8, 6 is right in the middle. The next one goes from 8 to 12, 10 is right in the middle. The next one goes from 12 to 16, and 14 is right in the middle there. Notice you're adding 4 to all the lower limits of each class, and you're adding 4 to the upper limit of each class. 12 plus 4 is 16, plus another 4 is 20. 16 plus 4 is 20, plus another 4 is 24. So how many hours do you exercise each week? And here's what our respondents told us. There were 72 that said that they exercised somewhere between 0 and 4 hours. It's the highest number of all of them, of all the frequencies. These would be the most, these are adult Americans apparently. And then the next highest group, there's a group 55 individuals that exercise between 4 and 8. So maybe that's about an hour a day. This might be an hour every other day. And these folks down here are workout enthusiasts, shall we say. They work between 20 and work out 20 to 24 hours, 2 people every week. 20, say 21, that's about 3 hours a day on average. A lot of working out. So I would encourage you to write the frequency distribution, even if the problem doesn't call for it. And if you see this, you'll be able to go back to draw the frequency polygon. So let's go ahead and now answer the questions. We've already talked about A. What is the class width? And we've identified it down here. So the class width is 4. The unit is hours. 4 hours. How many classes are represented? You can see that by looking in the table for the number of rows, 6 there. You can also see it, the middle midpoints. Not the first, not the last, but the 6 in the middle. What is the midpoint of the first class? See, it's unclear. If you look at the graph, it's harder to read, harder to interpret what the midpoint of the first class is. But if you have the class here and you see the midpoint, okay, now if you look on the graph, the first midpoint is the first point after the initial point on the horizontal axis. So the first midpoint is the x-coordinate of that point. So that would be 2. And the lower and upper limits, again, you have to go through a lot of this analysis that we've already done, but the lower and upper limits of the first class, there they are, 0 to 4. Okay, this one I'm going to ask you to put an answer in the chat. So C, what is the midpoint of the last class? And what are the lower and upper limits of that class? So there's 2 different questions, answer them both. First the midpoint, and then the upper and lower limits. So you want these 2, just like this, these 2 answers. Okay, it looks like the answers came quickly, and there's many of them all that agree. So that's correct. The midpoint of the last class, remember this one here is not a class. This is just a point that we put on the horizontal x-axis. There's the last class. The midpoint is 22. And the class lower and upper limits, 20 to 24. All right, D, go ahead and answer D. The hardest thing about interpreting graphs is to keep especially graphs like this, is to keep the x-axis and the y-axis so that you know the meaning of each. And so it says, what is the most popular? They're looking for the highest frequency. What is the most popular data value? Okay, now if you think about where this data came from, there would be 72 data values between 0 and 4. Now it very well could be that 50 of those individuals said 0. Don't work out at all. So we don't know how the data values are dispersed between 0 and 4, but we do know the midpoint is 2. So the way that you would answer this one, what is the most popular number of hours spent exercising each week? The most popular is this class. We don't know we don't know what are those, how many hours we're talking about. So I guess we'll answer this one as a class, somewhere between 0 and 4. It does ask for hours in terms of just, what is the frequency of the most popular response. And what is the least popular number of hours spent exercising? And it turns out that there's the number 1. So we would say 16 to 20. We don't know how many 16s, 17s, and 18s, and 19s are in there, but we do know that that's the most popular. Least popular. All right, and then which range of hours had 55 people exercise each week? Well, there you see 55 people exercising each week, and the number of hours there, 4 to 8. Now, you may have a couple of graphs in my math lab where they ask you to pick a graph from several graphs that they give you, 4 or 5. But many of your graphs will look like this, where you're just asked to, okay, here's the frequency polygon, interpret this about the graph. All right, so that's a frequency polygon. If we have more time, maybe we'll come back to another one, but we'll just stop with this one here. We'll have more practice over the next couple of days generating these graphs. Here's how you calculate the midpoint. The class midpoint is the sum of the consecutive lower class limits divided by 2. If you take 8 and 12, and you're wondering what this midpoint is here, you take the lower class limits, add them together, and divide by 2. It's like taking the average. So for a class midpoint, add 8 and 12, and then divide by 2. Plus 12, and there's the midpoint. All right, so if the numbers are messy, you can use this one, this formula. And it turns out that it's only the frequency polygon that uses the midpoints. So this is an ogive is the next graph. It's an XY graph, so all we have to do is, for each class, identify what the X is and what the Y are. And so over here, the XYs that we are going to plot, the X version Of course, it's an x-axis variable, and it turns out to be the upper limit of the class. So each one of the rows in our frequency distribution, cumulative frequency distribution, they will all have classes identified, and for each row, identify the upper limit of each class. That turns out to be the x-coordinate. And then the y-coordinate, in our previous graphs, the y-coordinate was frequency or relative frequency. We're going to define a new one now, and it's called the cumulative frequency. What we do with cumulative frequencies is we add up all the frequencies at that class and all the previous classes. So we keep a running total as we go from the lower classes up to the higher classes. Instead of just identifying the number in that class, we're asking how many are in that class or in some other previous class, lower class. In this graph, we also have a beginning point on the x-axis. And the coordinates there would be the lower limit of the first class would be the x, and then the y-coordinate would be 0. Now, we're not going to add an ending point to an ogive, just the beginning point. So lower limit of the first class and 0. So one additional point. By the way, I said I was going to show you how a histogram would look with respect to this frequency polygon. The first class goes from 0 to 4. So that's from about here to here. And there's where the first bar would be. If you continue this throughout, the histogram would look like this. And there you can see 1, 2, 3, 4, 5, 6 classes. And it turns out that they both use the frequency, so the y-coordinate of each one of those points in the frequency polygon correspond to the height of the bar. And there's the histogram. Now, we could do a table as we did in the previous one, because sometimes it helps us to interpret. But this point right here is the beginning point. So that one we're not going to count a class. This point is the lower limit of the first class. This is our upper limit of the first class. This is the upper limit of the second class, the third class, the fourth class. This over here is the upper limit of the last class. So if you wanted to count the number of classes, just count the number of dots, but don't count the first dot because that's one we just add at the end, the beginning point. There are a lot of points, so that means that there are a lot of classes. So I'm not going to do this entire table. Maybe I'll put it in the lecture notes, but I'm not going to do this whole table. I'll just do a couple of them. And I'm going to identify the points from the graph and then transfer those over to the table. I'm going to call that point 19.9 is the x. Zoom in a little bit. And it looks like it's 0. So, but 0 is, well, we'll just call it 0. It looks like 0, so we'll call it that. All right, that point right there is the next one. It looks like that point right there is somewhere between 19.9 and 29.9. So I'm just going to get the calculator out here and take the midpoint. Oh, you can see that? There we go. So it would be 19.9 plus 29.9. I'm using the midpoint formula here, and then I'm going to divide by 2. So right between 19.9 and 29.9 is 24.9. So that does not appear on the graph, that number, but that's in fact what it is. 24.9 And then you have to somehow, notice over here, these are relative frequencies instead of frequencies, cumulative frequencies. So as we're accumulating up here, I'm going to call that one about 0.01. It's about 1/10 of the way to 0.1. That point right there, it's clear to see what the x coordinate is. The y coordinate looks to be about 0.04. And then maybe I can write these one next to them like this. This is 34.9, and that's 0.10. This one here is 39.9, and it looks to be somewhere close to 0.18. Not quite close to, it didn't quite achieve 0.2. So you really have to be good at interpreting the coordinates of these points because they make a difference. So I'm going to do class. I'm going to write the upper limit because that's going to be the x coordinate of the class. And then I'm going to do cumulative relative frequency, 14.90. So this one goes from 14.9 to 19.9. So both the lower class limit and the upper class limit of the first class is identified there. And then the next one goes from 19.9 up to 24.9. The next one goes from 24.9 to 29.9, 29.9 to 34.9, and at some point you'll see the pattern there. Now the upper limit are these numbers over here of each class. So 19.9, this becomes our x, 24.9, 29.9, 34.9, and so on. And then the cumulative relative frequency would be what we use for the y coordinate on this graph. So I'm going to go to each point, 19.90. The next point is 24.9.01. The next point is there. That's 29.9 and 0.04. And then we get 0.10 and then 0.18. I guess I have one more there that I'll include. Now it turns out way down here at the bottom, the very last class goes from 94.9 to 99.9. So essentially you're going to have the upper limit is 99.9. You're going to account for all the possible graduation rates. And if you look at that last class right here, you can see it's up at 1. And that corresponds to 100%. And that would be the last class. All right, you can see that to actually fill out this table would require a lot more work. The number of classes corresponds to the number of points, except the first point is one we add. So we don't want to count the first point, but if you count all the points after that, you're going to have that many upper limits. And if you have that many upper class limits, then you have that many classes. So if we just count, ignore the first one, but then count the point 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So there are 18 points. We're going to ignore the first one. So there are 17 classes. And if you go from 34.9 to 29.9 and you do the subtraction, you get a class width equal to about 5. The difference between each of these is about 5. Now sometimes what we will do is write this last digit an 8, just so that there are no data values that would overlap. But the upper limit still would be the same as we have identified here. And the reason we might want to change this to an 8 is because if you get the data value 19.9, where are you going to count it? Are you going to count it in the first class or are you going to count it in the second class? So to avoid that, what we do is just reduce this one, understanding that it it's 19.89999. Anything less than 19.9, but 19.9 is the upper limit. Let's see if we have enough information to go and answer the questions. First one, A, what is the class width? Well, we identified the class width there. It's 5. Now, the beauty of the ogive is that it allows us to interpret a graph and ask how many data values are below a given x value. If you wanted to interpret that 0.18, you would do this. 18% of all data falls below 39.9. And I'm only using 39% here because the graduation rate is in terms of percent. If it was some other unit down on the x-axis, you would use that unit instead of percent. Saginaw Valley, as an example, where would they be? Well, I think Saginaw Valley has a graduation rate, 6-year graduation rate, 34% maybe. A third of students will graduate within 6 years. So they would be counted in this range here because their graduate is somewhere between 29.9 and 34.8. More specifically, 18% of all 4-year universities have a graduation rate less than, well, 39.9%, less than 40%, in other words. So an ogive allows us to make predictions based on, less than. How many data values fall less than this, as opposed to how many data values fall at this particular class. It's how many data values fall at this particular class or even something lower. Approximately 10% of all 4-year universities, that 0.10 corresponds to 10%. So using this example, approximately 10% fall less than 34.9. That's how we would interpret that. So approximately 10% of all 4-year universities have a graduation rate below 39.9%, about 40%. 1 in 10 colleges, 4-year colleges, have a graduation rate less than 40%. All right, next one. It says, what percent of all 4-year universities have a graduation rate less than 59.9? Now, eventually, you would hit 59.9 in that list. Eventually, you would. It's down a few classes. But what we can do to use the graph to answer that question is to go find the point that corresponds to 59.9. So we go over to the graph. Here's 59.9. And we're going to go up. And there it is. This point right here. The coordinates of that point are 59.9. And the y-coordinate looks like it falls right on a lattice line there. So that's equal to 0.6. And that means 60%. So you can just look at that point without generating this whole table, and you can answer the question in part C. What percent of all 4-year universities have a graduation rate less than 59.9? Well, it turns out that that is 60%. Because the y-coordinate equals 0.6. And they didn't ask you for what the relative cumulative frequency is there. They asked you for a percent. So you really should report your answer as a percent. All right. And finally, the last one, sometimes they'll ask you questions where you're going the other way. What percentage of 4-year universities have a graduation rate that's greater than something as opposed to less than something? All right, well, let's see how you would do that. 5% of all 4-year universities have a graduation rate above what level? If 5% above, then 95% below. So what we're looking at here is we're looking at the point that has a y-coordinate of 95. So I'm going to choose the one that I think is closest. I think that one right there is closest. That one right there is closest to 95. And the x-coordinate that corresponds to that point is 89.9. So we would say that 95% of all four-year universities have a graduation rate that is less than 89.9. And this means that 5% of all four-year colleges and universities have a graduation rate that is larger than 89.9. So here's the point. 95% fall below 89.9. So 5% fall above. And so there's the number that we want to identify. All right, so you have to see and construct and interpret lots of different ogives till you get it all until you get it right, because we're using a different x and a different y. So it's important to know as you're going into the graph what the x's mean and what the y's mean for that particular graph. Here's the 10%. I should have written this one down, but instead I grabbed that one for some reason. Thank you. 34.9. Okay, and the third type of graph that we're going to do today, the XY graph, will be time series. And what you do is you're not going to be adding any additional points here. You're just going to plot a bunch of points and connect them together. What's key here for a time series plot is that the x-coordinate will be the year. And the y-coordinate will be some y value. And it really depends upon the graph and what they're plotting. It could be population, it could be percent, it could be frequency, it could be a lot of different possible values. But what's key here is that the x-axis variable will be a year. So you'll see the years down here. Now the other thing is that for this particular graph, there are two graphs. A lot of times for a single time series graph, you're just going to see one. But if they want to show a relationship or they want to show a pattern between two different variables, then they will plot them both. And so the unemployment rate and the inflation rate. Okay, so this one down here is the inflation rate. Inflation stays relatively low and fixed under about 4%. And the unemployment rate fluctuates. And of course, you can see it was fairly low in the 2000s. And so highest was about 7 point, this is in the United States, 1992, 7% unemployment rate. Here's where we had a peak in about 2010. The unemployment rate was close to 10%. And you know now, because of COVID and everybody out of work, that the unemployment rate's probably up closer to 13% right now. So it's even higher than the highest one. So if we continued plotting the inflation rate and the unemployment rate over the next, say, 6 years, you would see that 2020, it would be even higher than the unemployment rate that you see here. I've identified a couple of points on the graph, and this is one of the skills that you're going to have. Sometimes if you want to begin these, just you won't need every single point, but good practice is just to write down the coordinates of each point. In 2011, the unemployment rate was 9%. Okay, so estimate the unemployment rate, and we will say 9%. And what year was the unemployment rate highest? That corresponds to the graph that's the highest from the x-axis, and there's the highest point, and that year was 2010. In what year was inflation the highest? Well, here's the inflation curve, and its highest point is this one, and that corresponds to 2008. The inflation rate was 4.2. I think now it's under 3. Fluctuates from year to year. It's pretty low right now. And what year were the unemployment rate and inflation rate closest, furthest? Well, it would be where the two graphs kind of come together here. So that looks like the closest, and there's another candidate for the closest, and there's another candidate for the closest. So just not too much difference between. You could take the percentage unemployment rate, subtract the inflation rate, and the number that's smallest would be the smallest difference between the two. And just by kind of eyeballing it here, I'm going to say it's here is the closest. And that one corresponds to the year 2001. And where the rates are furthest apart, okay, you're looking at this distance here from those two. That's a big one. Here's a big one. Here's a big one. Here's a big one. It's kind of, hard to tell exactly what the biggest jump is, but I think those are the candidates. And I want to say it's going to be one of these two here, just by looking at it, just by eyeballing it. So it's either 2010 or 2011. And I guess if we wanted to be, maybe you can just look at it, but we already have this one at 9, and this one is what, 1.7? So 9 minus 1.7 is 7.3%. And if we do this one here, that one looks to be about 2.6. And from 2.6 to 9.7, you get 7.1. So I'm going to say the furthest is this year right here, which is 2011. A lot of times you can tell just by looking, but those two were very, very close. Okay, in part E, we talk about the misery index. So the economy is doing pretty poorly if you have high inflation and high unemployment. If there's high inflation and high unemployment, then the economy is going to be doing poorly, so people aren't going to be doing as well. So what they want you to do here is add the unemployment rate and the inflation rate together, and then identify which year was the most miserable between 1999 and 2014. So for 1999, we have the unemployment rate and the inflation rate. And then in 2014, let's do the same. So this involves interpreting a couple of the points. Let's go over to 1999. We're looking at those two numbers. Let's estimate this one to be 4.2. And let's estimate this one to be 1.6. I'll call it 1.6. So if you take the unemployment rate and add the inflation rate together, you get the misery index, which is, what's that, 5.8. If you do the same thing for 2014, it's over here. So we're going to take those two numbers. This one here is, it looks to be about 6.5. And this one here looks to be about, I'll call it 1.6. So 6.5 and 1.6 is equal to 8.1. So we're just going to add these two to get that one. The misery index is defined as the sum of the unemployment and the inflation rates. According to the misery index, which was more miserable, all right? And so the higher the number, the more miserable. So we're going to select 2014. All right, the last one just says comment on the trend in the misery index. So if you wanted to do that, what you would need to do is go ahead and calculate the misery for all of those numbers. And so where you have both of those graphs lower, you're going to have a lower misery index. If the graphs are higher, you're going to have a higher. So since both graphs are decreasing here, you're going to see the misery index decrease until it hits probably a low somewhere in here. Then this graph goes up and this graph goes up to about 2010. So then the misery index increases to about 2010, and then, or maybe 2011, and then it looks like it goes down after that. So in words, you can say something like from 1992, if this is the misery index, and this is just a kind of a ballpark, but it's going to be up around 10 in here, and then it's going to continue to decrease to about the year 2000, kind of goes down, and then it's going to go up probably till about 2011, and then go down for the last couple of years. So maybe this is what it looks like. This is just a ballpark. If you really wanted to get a better curve, then you should actually calculate the misery index in each case. And I don't want to take time to do that now, but I think it's probably going to look like this. The misery index starts to go down to about 2001, 9/11 maybe. And then after that, it goes up, 2011. And then after that, it goes back down. So 2011 for the economy was not a very good time. Stocks were down, higher unemployment, higher inflation. Okay, so that's an example of a time series graph, and probably you'll be constructing a couple of those in Excel in your project. It's coming up. All right, so the last thing we're going to do here is we're going to look at a couple of examples where you have some graphs that are misleading. Now, if you're constructing a graph, it depends on what signal you want to send to folks. Do you want it to be misleading? Do you want it to emphasize a specific point aspect? Or do you want it to just be objective? And do you want it to convey the factual information without being biased in any way? So it depends on what your goals are, but just remember, in any graph, you can alter it to make it look misleading. So let's take a look at that. All of these graphs you're about to see are accurate. It's just that they're misleading in some way or another. A lot of times it's hard to see that it's misleading until you actually draw a graph that that would not be misleading. So I'm going to this looks like a bar graph. So I'm just going to generate a bar graph, and then you tell me, and I think that the bar graph that I'm going to construct here is one that's not misleading. We have 12-ounce beer. We have a 12-ounce soda. We have a cheeseburger. And we have a donut. And the scale should go from, what's unclear about this, or what's misleading about this, is that the different objects that they have are different sizes. You know, when we look at this graph, we don't know, are we supposed to interpret the height to the top of the bottle, to the bottom of the bottle? Are there bars there that make sense, and are they accurate? So let's go up to about 8,000, because the highest number. And again, this is the steps needed to burn calories. So if you wanted to burn off all the calories of a cheeseburger, you'd have to take 7,590 steps. Whereas if you wanted to work off a 12-ounce beer, you would need only 3,220 steps to burn off all the calories in a beer, and so on. That's what that means. All right, so I'm going to try to label the scale so that it's uniform. It's always difficult to do by hand. And that's why we use professional software like Excel to generate these graphs. But I'm just going to graph bars equal to these heights here, these number of steps needed. $3,200, 3,400, a little bit higher, 7,500, and 57. All right, so here are what the shapes look in proportion to one another if we start at 0. So what's unclear about the previous graph is, and I think another thing that you'll notice is that all the bars are different width to them. For example, the cheeseburger, the width is this, whereas the donut is only this. And so the width of the bars are different, and it makes the cheeseburger look so much bigger than the donut, even though it's just a couple thousand steps more. The thickness of the bars are misleading there, and that could lead someone to make a conclusion that's not correct. So make sure all bars are the same width, otherwise the graph is out of proportion. To improve the graphic, make all the bars that are the same. In the next graph, a nice bar graph, median earnings for females, 2007 to 2013. You see all of those years there, 2007 to 2013. Boy, it appears that the income for females is going down, decreasing quite dramatically. Is that what you see here? Making way up here. And it looks like, wow, the income almost looks like it's less than half 6 years later. And the problem with this one is that the vertical axis does not begin at 0. And because of that, it makes these small changes between different years to look dramatically larger than they really are. So here's what a graph would look like if you started at 0. Same graph. The graph is accurate. Let me just throw this one on here. See the two graphs? They are identical. This one, because we didn't start at 0, these little differences between, say, 22,500 and 23,500, $1,000 difference, looks dramatically different. It almost looks like they lost half of their salary going from one year to the next. But if you start the new graph off at 0 and go up to about the 23,500, this is what it looks like. And so there's very, very little difference in the median earnings of women between those years if we don't distort the graph like this. Now, if you wanted to create the graph and you wanted to say that women are earning a lot less these days than in previous years, this is the graph you'd want to use. But if you wanted a more unbiased description of the graph, presentation of the data, then probably this graph is what you would look like, what it would look like. This would be 23,500. This would be, 22,600 or something like that. But they're all very close to one another here, just not magnified. So how is the graph misleading? It's misleading because it doesn't start at 0 on the vertical scale. The graph seems to suggest that there's a dramatic decrease in female salaries over that 6-year period, when that isn't in fact the case. And then we redrew the graph starting at 0, and you could see that there's very little difference in the height of those bars. So there's very little difference in the median earnings of females over that 6-year period. Number 10, very similar. When you just look at the heights of those bars, it appears that in the year 2000 or 1992, it looks like the bar is 3 times as high as in 2004. But again, does not start at 0. So they'll ask the questions in a different way. For this particular one, it says, the safety manager at Klutz Enterprises provides the following graph to the plant manager, obviously a misleading graph, and claims that the rate of worker injuries has been reduced by 67% over the 12-year period. Does that graph support the claim? And so if you think that the bar 1992 is 3 times as high as the bar in 2004, then it does appear to be a 2/3 drop. But if you write down the actual numbers, this is about 0.202, and this one is about 0.180. So the difference between those two is, so what would that be? Right, so if you take these two numbers and subtract it, it looks like the proportion injured decreased by about 2 percentage points, 20.2% down to 18%. So if you take that 0.022 and divide it by the original amount, 0.202, and let me do this on the calculator, 0.022 divided by 0.202, you get 0.1089. So it's about 0.11 or 11% decrease. So this is what can happen when the graph is misleading. It looks like there's a 2/3 drop because this bar is 1/3 the size of this one, so 2/3 have dropped. But it was because the graph was misleading. And when we actually calculate the percentage drop, the amount of the drop divided by the original amount turns out to be only an 11% drop, not a 67% drop. So this worker's not impressing the boss at all. All right, let's do one last graph. We'll end on this one here. And if you are a baseball fan, then this displays every year the Major League Baseball will identify, each league will identify the most valuable player. And this data involves, okay, what position did that player primarily play? So if it was, say, Miguel Cabrera, when he won the most valuable player, he was a first baseman. So he would be counted in this grouping here, the first baseman, the 1Bs. So they did that over and over and over again for the last, since 1931. They've been keeping track of the position that players play who won the most valuable player. And this is an example of that you should just avoid 3D graphs, 3D pie charts in this case, because it's distorted. Because if you look at the third baseman back here, that's 11%, and then the pitchers up here, 11%, those should be the same size slice. And they're not. It looks like pitchers win the MVP much more often than the third baseman, but they should be the same. So misleading because of the 3D format. All right, so you'd say something like this. Those two 11%, and there's probably some other numbers that you could add up together to see the distortion here, but those two 11% should be the same size, and they're not. So it makes the graph look misleading. It makes it look like pitchers earn the MVP honor more often than third baseman, when in fact it's not the case. So instead, use a 2D graph. In this case, a two-dimensional pie chart. Then the 11% will look the same.